Hello friends, welcome back to our series Math for Machine Learning, and today we are going to look into the topic of linear dependency, and this will be the last topic in this section of matrix and vectors. Alright, so I've already written an example of three vectors v1, v2 and v3, and I want to calculate the determinant of this particular vectors. Now of course we cannot calculate determinants of vectors, but I can write these vectors in the shape of a matrix. So my A, I can write something like this: 1, 3, minus 2, and then I can say minus 2, minus 2, 0, and it will be 0, minus 1, 1. So these are nothing but each of the columns or the vectors that I have. Alright, so from my previous chapter I know that this can be calculated by first taking this row and this column, so that means I have 1 and then remaining 4 elements I have. So it's minus 2, minus 1, 0 and 1. Then I flip the sign and then I have this second column and this first element, which is minus 2. So I have minus 2 and the remaining elements are 3, minus 1, minus 2, 1, and then I have plus, and then I have 0 times 3, minus 2, minus 2, 0. I would encourage you to follow along with this example so that you get some practice. Okay, so that takes me to calculate the determinant, and we know that the determinant of a 2 by 2 matrix is multiplication of these two elements here, this one, and then minus these two elements. But in this case this is 0, so I can only keep minus 2 times 1, which is minus 2. This minus and this minus cancels out, so it becomes plus 2 times 3, and minus cancels out again, so 3 minus 2 plus, and this is entirely 0. So this becomes, I'll just write it for you here. So if a matrix has an element A, B, C, D, then the determinant is given by AD minus BC. This is just for your reference. Okay, so minus 2 plus 2 times 3 minus 2, which is 1. So 2 plus, this is 2 times 1. So this is equal to 0. That means the determinant of A turns out to be 0. Okay, so now that we have seen that the determinant of this matrix became equal to 0, and at A being 1, 3, minus 2, I'm just still repeating it here, minus 2, 0, and 0, minus 1 and 1. So interestingly, what I can see from here is, so these are my vectors, right? I call them vectors, or I call them columns of my data set. So I can see that if I have this element 1, 3, minus 2 times, say, A1 plus A2 times minus 2, 0 plus A3 times 0, minus 1, 1. Okay, so I'm wondering whether can I get a combination of A1 and A2 and A3 such that this expression here, this becomes equal to 0. So for that case I can have a set of three simultaneous equation, which is A1 times this is minus 2A2, and this is A3 into 0, which is 0, so I can write this is 0, and which can imply A1 is equal to 2 times A2. The second equation becomes 3 times A1 minus 2 times A2 minus A3 is equal to 0, and my third equation is 2 times A1 plus A2 times 0 plus A3 is equal to 0, and this can also imply A3 is equal to 2 times of A1. Okay, so let me take A2 equal to 1, so that means my A1 becomes 2 and my A3 becomes 4. Okay, so now if I plug these values here in place of a1, a2 and a3, let's see what result do I get. Okay, so if I plug these values here, so a1 is 2 and 2 times 3 is 6 and 2 times minus 2 is minus 4. This is 6. Okay, then I have plus a2 is 1, so it is minus 2. Then I have minus 2 again, and then I have 0, and then I have a3 as 4, so again this is 0, then this is minus 4 and this is 4. So what I get finally is 2 minus 2 is 0, 6, this is minus 2, 6 minus 6 is 0, and minus 4 plus 4 is 0. So that means I get a 0 vector. So which proves the point that I can find a combination of a1, a2, a3 so that this entire equation becomes a 0 vector, right? Now what does this imply? This implies that my vectors a times a1 times v1 plus a2 times v2 can also be written as something like minus a3 times v3. So that means this third column, now this can be any combinations, right? I can also put it this way: a1 v1 plus a3 v3 is equal to minus a2 times v2. I can change any of this and write this way. But what does this mean is that only out of 3, 2 vectors are sufficient to give me the information for the third one. So that means the third one is kind of redundant. Now as I was telling you the example of in one of my previous videos of the taxi fare, the predicting the price of a taxi fare depending on the distance and traffic, but in my data set if I have a distance represented in both in kilometers and miles, that means I can of course represent one of the columns by the other one. So for the miles one, and then I have a column for kilometer. So I know that 1.6 times my kilometer is nothing but miles. That means this column is linearly dependent on this column, or vice versa, right? So it gives me an indication that, you know, if the determinant of A is equal to 0, then the vectors or columns vectors are then linearly dependent. So this is one rule which you should keep in mind. So to summarize, we can say that just by calculating again the determinant of a matrix, and if it is equal to 0, we can say that the columns of that matrix A are linearly dependent. Okay, and if it is not equal to 0, then we know that they are not dependent, and then we have also seen other examples. So that means a determinant of A is a very good tool to find out so many things. Last time we saw about the matrix inverse, and today we are seeing it for column linearly dependency. Now in machine learning, if the columns of your data set are linearly dependent, as I shown you the example of miles and kilometers, there could be other columns which are linearly dependent. That means those columns are redundant and will not provide us any new information about the data set or the variation in the data set. Alright, so I hope you have learned something new today, and again this concept will be used in our future videos, and when we are deriving the linear regression and logistic regression kind of things. So I hope you will practice this, and please subscribe to our channel and pass this to your friends and colleagues who are also willing to learn the math for machine learning. Thank you and take care.